Mba633 instructional video prepared by Professor Amit Tata, School of Management, George Mason University. In this clip, we will see how to use Excel to perform ANOVA analysis, a one-factor ANOVA analysis, to help us test for the equality of multiple population means. The problem setting that we had worked on the previous clip is the one we will use again. There, if you recall, we were interested in exploring, based on sample data, whether a particular factor, specifically length of storage, had any significant impact on the response variable, which in this case was the calcium content of wheat that was stored. So our null and alternate hypothesis, so we had four populations here. So the null and alternate hypothesis were the means of all those four populations were exactly the same, the alternate being not all beans are the same. The way ANOVA got into the picture is that our approach to testing this hypothesis would be to reverse engineer and compute the population variance, which is the same for all four populations, assume the same for all four populations. You need that assumption in order to use ANOVA. So we reverse engineered this population variance. We computed the population variance, first assuming that the null is true, and second without assuming that the null is true, and try to see if we got values that were fairly close. In one case we got 10.7, in the other case we got 1.65, and they were statistically significantly different. So the F test that showed us that these two values for these two different estimates for sigma squared obtained by two different methods were statistically very different, so we ended up rejecting the null. So just recall, we'll keep coming back to these numbers in green, and now we will see how to reproduce these numbers automatically using Excel. And one objective of doing this in Excel is to show you the mechanics of carrying out ANOVA analysis, and the other, of course, is to understand the diagnostics. So the way you would carry out the ANOVA analysis in Excel is to click on Data, and then on Data Analysis, and then from the dialog box pick single factor ANOVA. Remember, we had only one factor, namely the length of storage that the wheat had been stored, and so we pick single factor ANOVA. And then the first input that you need to give is where's the input data. So here are our four samples, right? This is the samples. We got one sample each from our four populations, 0 months, 1 month, 2 months, and 3 months of storage. And the data is grouped by columns, of course, and we have labels in the first row. Since we are doing hypothesis testing, we must specify a level of significance. The default in Excel is 5%. And now we will put our output someplace. So let me just highlight a box over here. Oops, wrong place. So the output I want to specify to show up here in I1, and we just click OK, and there's the ANOVA output. So let me stretch out the column a bit, and we might be easier for us to read the output. So there we have our single factor output. So let me quickly point out, I think you can easily guess what these sets of numbers mean. The averages for the four samples. So 57.49, 57.95, 59.55, 60.33. These are the sample means, and the 1.89 through 2.11 are the sample variances. Just to show you very quickly, this is the average. So this is the sample mean for the first sample. You can see that this is identical to the value over here, the sample mean for the first sample. And then if I copy this formula over, these are the four sample means, and you can see them in the column over here. Okay, now let's compute the sample variances. This is the variance for the first sample, the sample from the first population. And if I copy this formula over, you can see that these four sample variances are exactly the sample variances in this last column. Now, right off the bat, you can see two numbers over here, 10.71 and 1.64. If you go back to our previous where we had computed things manually, I think you can see 10.71 over here. Okay, this was our estimate of the population variance, assuming that the null is true. And if you look at the 1.65, this was our estimate of the population variance without assuming that the null is true. So already you can see in the Excel output, you've got these two numbers right over here. Okay, so my main purpose is to now tell you where these three numbers come from. The SS, the abbreviation SS stands for sum of squares. Okay, so anytime you see sum of squares, you can see that you're talking about some kind of squared deviation, dispersion about the middle. So when you say squared what? Squared deviation from the middle. So sum of squares, where do these three numbers come from? And this will also give you another insight into where this what role this ANOVA plays, analysis of variance in our hypothesis testing. One thing to notice, of course, is that 32.13815 plus 32.91 is equal to 65.09. So just to show you, I add these two squares together and notice that it exactly equals the total. So before I tell you where these totals come from, arithmetically one thing you can see that the total sum of squares, TSS, total sum of squares, which is 65.03, has been split into two parts. One is sum of squares between groups, the other is sum of squares within groups. So where do these numbers come from? First of all, let's imagine that these four samples are really they're really just one big group. Let's assume that we don't have four separate groups over here. They are just one big group. What would be the grand average? So if we consider all 20 data points as one big group, then the grand mean or the grand average is simply 58.834. So now let's do the following. I take each data point, I subtract it from this grand mean, the mean assuming that all these data points belong to one group, and I square it. So this is where the SS acronym, the abbreviation comes from, sum of squares. So I'm taking each data value and subtracting it from the middle of the entire group of data. Okay, and I'll just copy this value over for all the other data points. 1, 2, 3, 4, 5, 6. So each of these numbers is a squared deviation, how much the value data point is away from the grand mean, and I squared it. Now let's add up these squares. So you can see the 65.03918. Do you see this is exactly the total that we have over here? So that's what the total sum of squares means. So it is the how far each data point is from the grand middle. Okay. Now let's imagine that we have each data point and see how far it is from its own middle, the group, its own middle. So 57.49 is the middle of the first group, isn't it? So I'll just see how far the first data point is from the middle of the first group, and I square that. Okay, so I copy that down to the remaining 5 data points for sample number 1, 2, 3, 4, 5, 6. Okay, then I go to the second group and I do the same thing. How far is this data point, 58.87, from the middle of the second group? So notice that now I'm treating each sample as a separate group instead of treating all 4 of them as one big group. So I subtract this, square it, and I think you know where I'm going with this now. I just copy this formula down. I do the same for the third group. How far is this data point from the middle of the third group? Let's copy this down, do the same for the fourth group. How far is the first data point from the middle of the fourth group? Copy this over, and now sum all these squares up. And look at the value that I got. It is 32.90103, and that's the within group sum of squares. So this is the variability within each group. If I treat each group separately, this is the variability within each group. Okay. Now imagine what would happen if all the data points, imagine that all the data points in the first sample, if all these 6 values in the first sample were exactly at the centroid, at the center of the first sample. So every value in the first sample was 57.49. Okay, I'm essentially trying to find out how distinct each of these groups are. So let's take the middle of this first group, which is 57.49, and I see how far it is from the grand middle. Okay, and I square it and I multiply by 6. So before I hit enter, let me explain why I did that. So I'm trying to imagine that everything, all the data points for the first group are concentrated at the center of the first group. All the data points for the second group, second sample, are concentrated in the middle of the second sample. All the points for the third sample are concentrated at the middle of the third sample. And now I will try to see how far apart each of these the centroids are of each of these groups. Okay, and since there are 6 data points in each group, I weighted by 6. Okay, so I need to make this value, okay, it's already absolute. So let me copy this formula over and sum these 4 values up. And notice what we got. We got 32.13815, which is exactly this value, 32.13815. This is between groups. Notice this last calculation that I did, I treated each of the groups separately and tried to see how far they were from each other. So this is the variability between groups. This is where this is the physical interpretation of these 3 numbers. Okay, so I've been able to take the total variability and split it into 2 parts, between groups and within groups. This is what the analysis of variance was able to tell us. Okay, now if we take the the degrees of freedom, I will not get into a detailed description of the basis for this degrees of freedom. I'll just tell you that the degrees of freedom for between groups is simply number of groups minus 1. So we have 4 groups, and hence the degrees of freedom here is 4 minus 1, which is 3. And the degrees of freedom for within groups is the total number of data points minus the number of groups. So the total number of data points we have for our sample here is 6 times 4, which is 24. We have 6 data points for each sample, 4 samples, so 24 data points. There are 4 groups, so 24 minus 4 is 20. This is where this 20 comes from. Now MS stands for mean squared. Mean squared is simply sum of squares divided by degrees of freedom. So this 10.7122, just to show you the calculation, it would be the between group sum of squares divided by the degrees of freedom for the sum of squares. Okay, similarly the 1.64, where does that come from? It is the sum of squares for within groups divided by the degrees of freedom for within groups, 1.64. The physical interpretation of 10.71 and 1.64 you saw from our previous video is that these are 2 different estimates of the population variance. This one, the 1.64, is without assuming that the null is true. This 10.71 is assuming that the null is true. So now we have to check statistically whether 10.71 is very, very different from 1.64. Okay, we can't just eyeball it and tell it. The usual, the the test statistic that we use to check whether these two are very different is the ratio of the two. So this value 6.51, the F statistic is simply the mean square between groups divided by the mean square within groups. Okay, so you can see it's exactly 6.51. Okay, and what about the p-value? The p-value is the probability of getting an F statistic of 6.51 or higher if the null were true as an equality. So to calculate the p-value, I simply use fdist. What is the likelihood that I would get a F value of 6.51 or higher? Degrees of freedom for the numerator is 10.71. So the degrees of freedom for the numerator is 3. That for the denominator is 20. That's where the 20 came from here for within groups. Okay, and there's your 002982. F critical, how do you get your F critical? This is the value of F, that this is the how high the F statistic would have to be, is the minimum value that I need for the F statistic in order for me to say that it's extreme enough and that these two variances that I computed are not the same. Okay, so my F would have to exceed F critical if I am to reject the null. So how do I get the F critical? Remember, the default level of significance was 5%. So I use F inverse of 0.05. Degrees of freedom is 3 for the numerator and 20 for the denominator. There I get my 3.098. So any F ratio that is more than 3.098 for this problem setting would lead me to conclude that the two variances that I computed, two different estimates of the population variance that I computed, are significantly different. In this case, the value of F that I got is substantially higher than the F critical. So whether I use the p-value method or the critical value method, I end up concluding that I reject the null. And what was the null? The null was that the means of the four populations are identical. So I reject that and I end up with the conclusion that I had, the same conclusion that I had manually, namely not all means are the same. So the factor length of storage does in fact have a significant impact on the response variable, which is the calcium content. So this is your ANOVA analysis. This is actually how you would do it in Excel, and you would not do any of these manual calculations, but I have done them just so you know where all the Excel output comes from, what it physically represents. You must be able to give a physical interpretation for each and every number that you see in the ANOVA output.